All right, most of this lesson is pre-calc review. Refreshing your memory on what exactly it means to have a inverse. And we're going to get a little picky on terminology here because I know that in pre-calc you use the term inverse, all loosey-goosey type stuff, and we're going to have to lock that down. So, inverse functions, we are going to talk about, there's an important phrase up there, I'll read it to you. Verify that one function is an inverse function of another function. So we're going to make a discrepancy, we're going to make a distinction between having an inverse and having an inverse function. They're a big thing, or a big difference. All functions have inverses. Not all inverses are functions. Does that make sense? In pre-calc, you probably just talked about inverses and didn't care too much about whether or not those inverses were functions. Here, we need to worry about that, which is exactly what my second point says. And then, of course, we're going to talk about the derivatives. So not up until step 3 do we actually do some calculus. Before that is I'll just review stuff. And then, of course, the background would say you should try to eat healthier foods. Just say. No judgment. I'm just trying to help. I'm not trying to imply anything. I'm just saying you might eat healthy foods now, but you could eat healthier foods.
Does that involve calculus?
It could. If you don't eat healthy foods, you could use calculus to track your rate of growth.
Matthew's brain exponentially decays.
You could also use calculus to find the volume of a donut. Just saying. So blah 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 blah. Again, review. First of all, notice the notation. That is not the f to the negative 1 power. That's the notation for inverses, not reciprocal functions. That's not 1 over f. That's the inverse. A thing that will be relevant for you is that first statement, and I'm sure you've heard this before, that the domain of the function is the same as the range of the inverse, and the range of the function is the same as the domain of the inverse. And then the second thing you knew already, they undo each other. So if we take a function like a square root function, the inverse of a square root function would be a squared function. The inverse of addition is subtraction. The inverse of multiplication is division, etc., etc., etc. They undo each other. So notice these two last sentences at the bottom here. If you take f of the inverse of x, you'll end up back at x. If you take the inverse of the function of x, you end up back at x. And we're going to use that information to verify whether or not two functions are inverses of each other, not necessarily to find those inverses. We will do a little bit of work of finding inverses, but that's not really the focus for today. And you know all this, right? Sure. Yeah. Okay. So here's two functions. I'm suggesting that those functions are inverses of each other. In fact, it tells you, show that they are inverses of each other. And so we do a little substitution here. We're going to see what is f of g of x, and we're going to see what is g of f of x. Okay, so I'm changing the notation a little bit. I'm not using f and f inverse. I'm using two functions which I think might be inverses. Okay, the first one in red, does that mean put f into g or g into f? G into f, good. So 2 times this mess raised to the third power minus 1. And you can see quickly that this becomes a little ridiculous. Cubic root raised to the third power cancels. That goes away. 2 on top cancels with the 2 on the bottom. X plus 1 minus 1 equals x. Woohoo, good to go. Second one, put f into g, the cubic root of 2x cubed minus 1 plus 1 all over 2. This one goes quickly, cancels, 2's cancel, the cubic root of x cubed is x. Kaboom. They are inverses of each other. And again, some pre-calc review there. Questions? Am I going too fast or we're good? Good, good. That's all I need is one to move on. Here we go. Okay, this is huge. And I don't know if you talk about this in pre-calculus. And we're going to use this later when we get to the calculus. There's a little nugget of information about inverses, and that is, if you graph a function and its inverse, they are reflections of each other over the line y equals x. Have you ever heard that before? You have. Good, then your pre-calc teachers did a good job. Has anybody not heard that before? Excellent. Okay, then I didn't give them enough credit. We're going to use that idea to do some calculus later on, but before we get to that, we need to talk about something else. Let's suppose there's a point on this gray function labeled AB. If I reflect the point AB over the line y equals x, I'll end up over here. Because again, they're reflections. What's the coordinate of that second point? Emma?
BA.
BA, very good. When you reflect a point over the line y equals x, the coordinates, the x and y coordinates, switch locations. Okay, so xy goes to yx, AB goes to BA. We're going to need that later on. Okay. Rolling right along. Oh, by the way, is that black graph a function?
Yeah.
How do you know?
That's a vertical line.
The vertical line test. Is that you, Kate? What does that mean?
It just only hits it once, like it doesn't overlap.
For any vertical line test. For any vertical line, I should say.
Oh,
Bless you.
I don't know, I'm getting confused.
Anybody help clarify?
The vertical line test,
Right, yeah.
as long as it doesn't have more than two, I think x coordinates, or one of the coordinates, yeah, it can be more than two on like one vertical.
For any vertical line.
Right.
So no matter where I draw a vertical line, it's only going to hit that black function in one spot. Is that what you're saying, Katie?
Yeah.
Good, therefore it's function.
Yeah.
Perfect. What about that gray line? Is that a function?
Yeah.
No, yes.
Yeah.
Well, it's a little shaky in that area around -1, isn't it? Yeah, what's going on there? Is that, is it, I don't know. We'll come back to that. But for the most part, it would pass the vertical line test except for that weird area there. But if that weird area hits in more than one spot, it's not a function. Okay. I did that already. So here we go. Horizontal line test. Now, Katie, you talked about the vertical line test, which tests whether or not a function is, whether or not an equation is a function. Yes? Okay, so if I take a vertical line and I reflect it over the line y equals x, that vertical line becomes a horizontal line, which leads us to the horizontal line test. The horizontal, have you heard of this before, by the way? Did you do this in pre-calc? No, this is new? Interesting. The horizontal line test will test whether or not the function has an inverse function. Okay, so let me say that again. Does the function have an inverse function? So all functions have inverses. You can take any picture and reflect it over y equals x and get another picture. The question that we're going to have to deal with is that reflected picture also a function? Okay, and we can do that using the horizontal line test. So we don't have to bother graphing it and looking at the reflection. We can look at the original function, which is what that says. It's basically the fancy schmancy calculus talk on what makes the horizontal line test work. However, there is a phrase in here that comes up a lot, and I don't know why, but this phrase, strictly monotonic. I guarantee you've never heard that before, yes? Okay, good. Strictly monotonic means it's always increasing or always decreasing. And the reason you haven't heard that is because it's pretty much a calculus term. Is this function always going up? Is this function always going down? If it is, then it's said to be strictly monotonic. And that becomes relevant when we start doing some of the calculus stuff coming up. So a function like x squared is not strictly monotonic because x squared increases then decreases. Or decreases then increases depending on which way it faces. A line would be strictly monotonic. It's either always going up or always going down. Go back to this picture. That black graph is strictly monotonic because it's always going up. As is true about the gray graph, always going up. Okay? So, simple question. Do these functions have inverse functions? Yes, we know that they have an inverse. What we're concerned about is whether or not that inverse is a function. So first things first, get out your calculators or your Desmos or whatever you want to use. Let's start with A, graph A, and tell me if that will pass the horizontal line test. Okay, so again, I'm going to talk while you're graphing. Vertical line test tests whether or not a graph is a function. Horizontal line test tests whether or not the inverse is a function. We're going to focus on the horizontal line test. Does the graph of A pass the horizontal line test? Yeah, good. No problems there, right? So it should have, by the way, for those of you that didn't graph it, it looks something like this. Does it pass through the origin? No, it's over to the right a little bit? Yeah. So it looks something like this, right? Okay, good. Passes the horizontal line test no matter where I draw a horizontal line through it. It will only hit in one spot. Okay, so that's the pre-calc approach to it. Let's take a calculus approach to it. And in order to do that, I have to ask a simple question. How do I know, forget about this picture, let's pretend we didn't have a graphing utility. We don't have the ability to graph. How do I know if that function in step A, or problem A, is always increasing or always decreasing? Are you raising your hand, Mr. Zimmer?
Yes.
Please share.
Well, if you find the derivative and set the derivative equal to 0,
Okay,
you can find if it changes direction or it's horizontal.
perfect. Good. So what if, all right, so let's do that. F prime of x, 3x squared plus 1. So you're saying set that equal to 0, solve, find your critical points, put them on number line tests.
Yeah.
Good. Perfect. However, not even however. Well, we'll say however. There's an easier way to do it. What can you tell me about that function? Sorry, that derivative. Thank you.
Is it for everyone?
Good. Keep going.
So it goes. So the slope of the initial function goes up and down.
So it's upside down or right side up?
Oh no, I'm talking about anyone.
I understand. You lost it there. Alice,
The inverse can't be a function
why?
because it won't pass the horizontal line test.
What won't pass the horizontal line test?
The original, like the derivative won't pass, which means that the inverse won't pass the vertical line test.
We don't care about the derivative. We care about this. So a horizontal line test deals with the original function. And that was the picture I drew before. Okay, so I'm taking two different approaches to this. One is the graphical approach. Doesn't pass the horizontal line test. The other one is calculus. Can it? Go ahead.
Is it because like the slope of the derivative is always increasing?
I think what you're saying is correct. I just think you're saying it a little sloppily.
Okay.
Matthew.
It has no x-intercepts, so the initial function never changes. It never like loops over itself.
But it does. It's parabola.
Or wait. Yeah.
Can that derivative ever be positive?
It's always positive.
It's always positive. Can it be negative?
No.
No. Okay, so that's an important thing. Now, Mason, what you said is 100% accurate. I could solve for the critical points, which would be plus or minus the square root. No, there would be no critical numbers. Can't solve that, right? Because it would be square root of a negative number. Then we're screwed. But if it was something where we weren't screwed, we could still solve for critical numbers, test it, and when you test it, it's going to be plus plus. The other thing is, if you're a little sneaky about it, if you look at this, you can recognize that that value can never be negative. Do you all agree? Yeah, no matter what I put in for x, I'm going to get a positive value. Since it's always positive, it's strictly monotonic, and if it's strictly monotonic, then the inverse is a function. And you know what's going to happen in part B? It's the exact opposite of what's going on here. So, just to keep things above board, graph part B, and look at the graph and see what it looks like. That's a dumb statement. Just graph it. So you see a more traditional cubic function that does not pass the horizontal line test. Right. I think it looks something like this, yes? Okay, doesn't pass the horizontal line test, good to go. From a calculus standpoint, f prime of x is equal to 3x squared minus 1. That function can be positive or that function can be negative, and therefore not strictly monotonic. And no, the inverse is not a function. It has an inverse. We could find it. We could graph it. We could reflect that over y equals x. It just won't be a function. Okay, does this all make sense a little bit here? Do you understand what we're doing here? Yes or no? We're good? Any questions? Okay. So the only thing new here, theoretically, is the idea of using the derivative to see whether or not the inverse is a function. Okay, you're good to go with the graphing and the horizontal line test. Just this pesky little guy of taking a derivative and seeing whether it's always positive or always negative. Remember, squaring functions always makes it positive. The same is not true about odd functions. If you raise something to the third power, it doesn't guarantee that it's positive. It can be positive or negative. Okay? Good. And we did both of those. So we did the HLT with your graph, and then we talked about the derivative. Lovely. Okay. Now, if you want to find the inverse, I know you did this ad nauseum in pre-calculus. If you actually want to know what the inverse function is, you'll recall this process. Switch the x's and the y's, solve for y, and whatever you end up with for y is your inverse function. But again, you've done that quite a bit, so that's not, I don't really want to focus on that too much. And I think you're all pretty good on that. I might have an example here. I don't remember if I kept it in there or not. You do recall doing that, right? I did put an example in there?
Yeah.
No.
I'm pretty sure.
Yeah, okay. I mean, all right. I'll do it too. This is y equals the square root of 2x minus 3. Switch the x's and the y's. X equals the square root of 2y minus. You can hear how excited I am about this. Again, not real exciting. I intentionally picked an example that's really easy. They get in a little bit more complicated, but it's still the same process. Switch the x's and y's, solve for y. You got it. If you wanted to check that then, you could take that inverse, plug it back into the original function, but again, it's repeating the example that I did earlier, so we don't need to bother. Let's do some calculus. This will be fun. Oh, look, I have the solution. Yeah, okay. F is strictly monotonic and has an inverse function. I didn't bother checking that, but we're good to go. Okay, great. Excellent. There you go. Check it in. Okay, excellent. Here we go, calculus. This will be more interesting. I'm going to show you two techniques. Many of you will opt for the first technique, which is pure memorization without an understanding. However, I'm actually going to switch the order. I'm going to go to the end of the slideshow and show you a different way to look at it versus the formula that comes first. So we're just going to fly through this quickly and get to this guy. Whoop, that guy. Okay. Our ultimate goal here is to find the derivative of the inverse of a function. So obviously, I'm going to actually talk about three methods. The one method you're not going to use is, you're not going to find the inverse function, then take the derivative, then plug in a number. We're going to try a different approach. So let's suppose I have a function that looks something like that. Okay, we'll call that f of x. Put arrowheads on it. Life is grand. And then I have an inverse function. We know already that that inverse function will be the reflection of that blue function over the line y equals x. And so we will get something that looks like this. Well, kind of like that. All right, we're going to go with it. And the problem is going to say something like, I would like to know the slope of the derivative of the inverse at this point. Wherever that point is, let's call it point AB. And we can do a whole bunch of work with the inverse function. You can find the inverse function. You can plug into the formula. But I'm going to show you an alternative approach. And the alternative approach is to work with the original function. If I have the point AB there, we talked about this already, it would have a corresponding point over here, which would be at the point BA. And this graphic method, which doesn't involve drawing a graph, it's just understanding what you're doing, involves one simple fact, which I'll get to in a second. I would think that if I gave you a function and asked you what is f prime of b, you could do that, could you not? What am I doing? If I ask you for f prime of b, I'm asking you what is the slope of the tangent line to the curve at b. I'm asking you for the slope of that line. You with me so far? But that's not what the problem is asking. The problem initially is going to ask what is the derivative of the inverse function at a. This is what we're starting with. And my argument is, don't do that. Work with the original function. So if I know the point AB is on the inverse function, then I know the point BA is on the original function. This is pretty easy to do. Take the derivative, plug in B. But really, what I'm asking initially is, what is the slope of that line? That's the original problem. And here's the kicker. The only thing you need to remember here, other than what we're talking about, is the relationship between these two slopes. And it doesn't look like it in this picture, but we'll call this slope M1, and we'll call this slope M2. M1 is equal to the reciprocal of M2. Not opposite reciprocal, just reciprocal. So the slope of the tangent line to the function is the reciprocal of the slope of the tangent line to the inverse function. Finding M1 should not be a big deal. Once I find M1, I'm good to go. Because then all I need to do is just flip it over. Doesn't involve finding an inverse, doesn't involve remembering a formula, which I'll come back to in a second. It's just a matter of doing some straightforward, simple calculus. Now notice in my picture they look like they're parallel. That's just a fluke of the way I drew the picture. Okay, who's thoroughly confused? Oh, good. That went better than I thought. Or you're afraid to admit that you're thoroughly confused. It'll make a little bit more sense in an example. Okay, so let's do this example. So I started with a function f of x. I want to know, first of all, I have to figure out I'm going to end up finding this. This is the ultimate part of the problem. What is the derivative of the inverse at the point x equals 3? So what I need to know is what's the corresponding y value. I know that if I'm doing f inverse of 3, I would get some value. This implies that f of that value would give me 3. That has to do with the switching the A and the B business. So I said, what value of x will give me f of x equal to 3? So I set that puppy equal to 3, and I did some math magic, and I ended up with 2. You'll have to trust me on that. That's not a crucial part of the problem. But this allows me to fill this in and to fill that in. So what the problem is saying is, what's the slope of the tangent line to the inverse at when x equals 3? So I'm going to change the problem completely. I'm just going to ask myself a simple question. What's the slope of the tangent line of the function when x equals 2? Because these 2 points, 3, 2, and 2, 3, correspond between the function and the inverse. Once you understand that, then it's easy. In other words, I'm looking for f prime of 2. Well, that would be 3/4 x squared plus 1. Actually, let me get rid of that. X, so then f prime of 2 would be equal to 2 squared 4 is 4. Okay, makes sense so far? The last thing we need to do is flip this over. So f inverse prime of 3 would be equal to 1/4. Okay, so first thing you have to recognize is that relationship between 3 and 2 and 2 and 3. Then you take a simple derivative, plug and chug, and the last thing is remember to flip that puppy over. Even though your head's about ready to explode in that explanation, I still find it easier than the formula. However, some of you are just going to go home and memorize the formula. That's okay. Whatever works for you. So what's the formula? The formula is right there. So if I'm looking for the value of the derivative of the inverse of the function at some point, in the example I had 3, then I have to find the value of the inverse for 3. Then I have to plug that into the derivative of the function. So you're kind of going about the same method. The thing I don't like about this formula is that a lot of times it's going to require that you find the inverse function. To me, that's a lot of work. Whereas I'm pretty good with visualizations, and that... Where's my picture? I lost my picture. Oh, it's further down. This picture, where is it? Come on. That picture makes more sense to me. But again, whichever one works better for you. If you just want to plug into a formula, it's not a matter of just plugging into a formula. But if you want to plug into a formula, you can. That's okay. I find the graphical approach a little bit easier. Good news, bad news. The good news is this doesn't happen a lot. Inverse functions are not a crucial idea in calculus. The bad news is it's a little nasty. The work itself is not nasty. Understanding what you're doing to get that work gets to be a little tricky. Okay. If the function is easy and you know what you're doing, then by all means, find the inverse, take the derivative, plug and chug. That's okay too. That, however, breaks down in a problem like this. I don't know how to find the inverse of that function. If I switch x's and y's, I can't solve that. I don't know how to, nor do you. So you got to find an alternative method, either the formula or the graphing technique that I talked about here. Okay. Again, reciprocals, not opposite reciprocals. They're not perpendicular. They're just reciprocal of each other. Okay? All done. I fixed it, now we're back on track. So day 52 should be day 52. And again, remember, it's a combination of the two things. Let me stop this.